Yeah, so with the methane, there are two issues. One is this methane burst. And as the Arctic warms, and the Arctic is warming 3 times faster than the rest of the planet, the permafrost melts. And the land permafrost, you sometimes see these big 100-meter diameter holes where the methane melted and pretty much exploded. But even worse than that is under the ocean, where it's been frozen for hundreds of thousands of years. As the sea level rises up and down, you get grasslands that then get buried under the water and then get frozen. When the ocean is no longer covered with ice during much of the summer, and it gets up to 10 degrees Celsius or 50 degrees Fahrenheit, and the undersea ice melts. And that has the possibility of releasing huge amounts of methane. And that's the worry, because that sudden methane will warm the planet tremendously. And it's the sudden warming that kills off species. So that's the reason I got involved in methane. The other part of methane is just that it warms up the planet a lot. And about almost a third of today's warming is due to methane in the atmosphere. So the two problems that methane causes, one is overall warming, the other is a sudden warming that causes extinctions, which hopefully we can avoid our own extinction that way. It's funny to say it so calmly, but I've been working on this so many years, I'm pretty resigned to that possibility being real. Then the prevention of it is rather exciting. And methane in the atmosphere oxidizes gradually due to sunlight and various chemical reactions. And what we call the half-life is 8 years. And which means that if you put a gallon of methane in the atmosphere, in 8 years, about half of it would have been oxidized to CO2 and water, and only half would remain. Then we can double the oxidation rate and make that down to 4 years by doubling the amount of reactions that are oxidizing it. And we've learned how to do that using iron chloride. There are some other ones that are actually being discussed now as well. But using the specific iron chloride pathway, the cost of doing this is only about $1 billion a year. And so for $1 billion a year, a reinsurance company, for example, could cool the planet and also ensure that the methane burst doesn't destroy their customers. And so it's really could be good for their business. It's obviously also good for families to do that.
Are there any, can you cite any examples of where people are working on this process as an experiment where this is in process?
Yeah, there are a couple of scientific groups working on it. I'm working on it myself here, waiting till I get funding to get a better qualified scientific group to do it. The original paper on it was written in 2017, 5 years ago. And it's so out of the box that no one has done any significant funding for it until the last year or so. Given my commitment to giving a world that we're proud of to our children, I put in the first $50,000 about 2 years ago to get the academic work started.
Fertilization.
Yeah, so when it comes to removing CO2 and restoring CO2 to levels that humans have survived long term, the most obvious way for me is using the same method that nature has used before ice ages, and that's iron fertilization. And I describe that in terms of the ocean. When I think of it, I tend to think of the ocean off Hawaii, which is very blue. And it's beautiful, but it's not green. And we know that it's chlorophyll that turns the ocean green, which also removes CO2. And then the question becomes, how do you turn a blue ocean green? And because there's obviously a lot of sunlight and a lot of water, the missing nutrient is, in most cases, it's iron. And the reason it's iron is that iron tends to not dissolve in water, and so it tends to fall to the bottom. And in nature, before ice ages, a lot of that iron will come in the form of dust storms and occasionally volcanoes. The dust will have some iron in it. We can do the same thing, and it's been demonstrated about 10 years ago that you can use iron ore dust, which very fine, and over a limited area of the ocean, usually in an eddy, so the circulation keeps it contained, and then it'll stay there for maybe half a year, and you get a lot of phytoplankton, a lot of algae growth, which is fish food. And so you get fish growing, and eventually everything dies and sinks. And when it sinks in the ocean, there's very little oxygen in the deep ocean, and it doesn't rot. And the big advantage over the trees that we usually hear about as a solution for climate is trees, of course, die after a few decades, but then they rot, and the carbon goes back into the air as CO2 again, and that doesn't happen in the ocean. So with the iron fertilization, what's amazing is over the billions of years of nature, it's become very efficient. It takes about a hundredth of a teaspoon per square meter of this iron ore dust to provide the nutrition required. And if you think about sweeping your front porch, in the morning, you realize that that's a lot more than a hundredth of a teaspoon. So the amount of dust involved is much less than you see on land.
And limestone?
The second approach, which is limestone, is modeled after what nature does over long periods of time, and the limestone on the planet is mostly under the ocean and in the seafloor. It consists of skeletons and shells of animals over hundreds of millions of years. If you've seen a picture or even seen the White Cliffs of Dover, that is the limestone that nature has collected. A company here in Silicon Valley called Blue Planet Systems has developed the ability to manufacture limestone very much like an oyster does. And if you're like me, you mostly see oysters in a restaurant, but you see this beautiful shell and this little creature which forms the shell. And the chemistry is fairly simple. To get the right hardness is difficult, but they've learned how to do that. So what's very exciting about this is they can now make synthetic rock, synthetic limestone, which by weight is almost half CO2. So we could sequester all of our excess CO2 in our built environment under our feet by using the synthetic limestone from now on for the concrete in our roads and our buildings.
Great, okay. And then the first one, the ocean.
Let's see. Then the last one is, the fourth one is, the last one is the seaweed. And this is a variation on the phytoplankton, on the algae. And it's the same principle that the ocean is huge, there's a lot of sunlight and a lot of water and nutrients. And with the seaweed, what they do is they, rather than adding iron to the surface like with a dust storm, it upwells it. Again, a little bit like whales used to do. We removed about 95% of the whales on our planet, used them for oil before we discovered petroleum. And they would get nutrients from the deep ocean, and then they would they would poop it near the surface. And the seaweed system does the upwelling with a pipe and a solar-powered pump, and then grows seaweed, because that grows extremely fast. It's the fastest growing plant on the planet, primarily kelp and sometimes sargassum. So then when they grow it, about half of it falls back down into the ocean, and then they harvest the other half and sell that to pay for the process, because the chemicals in it, they're valuable for food and fuel, feed for animals, and amazing chemicals for manufacturing. There's a synthetic leather that comes out of some of the seaweed. Well, that can be made from it. But in all of these cases, you've got a product which has a customer. So with the limestone, of course, we pay a lot. We pay $1 trillion a year is the market for rock for these roads and buildings. So it's a great market. It's the right size. With the ocean fertilization, when you fertilize and restore the ocean, you get a lot of fish growing, and that the fish market is more than plenty to pay for the small effort of applying the iron ore dust.
In broad brushstrokes, just going to stop and start